In this video, we'll talk about using spherical coordinates to help solve difficult triple integrals, especially those that involve spherical wedges. But first, let's review a little bit about what we covered last time in class. So last time we were talking about the similarities between polar, cylindrical, and spherical coordinates, where spherical coordinates are very specific. Each point in three-dimensional space is defined by three parameters. One is the distance from the origin to the point, and the other two in spherical coordinates are defined using angles. So just as a reminder, theta is an angle to the polar axis, or within the xy plane, the projection of the point to the xy plane and its radius. Essentially, theta is exactly how it is in polar and cylindrical coordinates. Phi is kind of the new angle, and that is the angle that the z-axis forms with the new polar axis, or I guess we could call it the spherical axis, essentially the axis that goes from the origin to our point. And what we talked a little bit about was the relationships, the formulaic connection between xyz and rho, theta, phi. And essentially just a little bit more trigonometry to get there. We also did a few examples of taking points in each of those coordinate systems and converting it from one to the other. So we took a spherical coordinate, turned it into rectangular coordinate xyz to see, okay, yes, this is in the first octant. And we also took a rectangular coordinate, which was in the fifth octant, I believe. Well, actually, since it was 0, it's not in any octant. Regardless, not important. We took a point which contained xyz and converted it to rho, theta, and phi, again, using those relationships. In this video, we'll focus mostly on applying all of this to solving integrals tactically, much like how we've done some examples of double integrals in polar coordinates and triple integrals in cylindrical coordinates. But anyways, sort of summarizing, spherical coordinates are a different three-dimensional variant based on two angles and a radius. There's a relationship between the differential volume and the... sorry, my dog let out a big sigh. Got distracted. That's the Winston Cam. He seems to be doing a lot better, for those of you who... I know you guys have been asking about how he is. Anyways... but it involves rho, theta, and phi. Again, kind of like how in rectangular coordinates, volume is just the product of dx, dy, and dz. The translation into spherical coordinates requires something which we call Jacobian. And in the next couple lecture videos, we'll talk a little bit more about why. For now, you'll just have to take my word for this transformation from volume into these coordinate systems. But essentially, because we have two angles which are both measured in radians, non-unitary measurements, we need to multiply by rho in both cases to ensure that our volume has a three-dimensional units. And the sine theta is also important, or sorry, the sine phi, is important for compensating for phi. But anyways, how we're going to start off our exploration into triple integrals using spherical coordinates is starting with kind of the most simplistic type of region E, which in this case is sort of like we talked about a polar rectangle, which is sort of like a semicircular kind of piece. A spherical wedge is defined to be a set of points in spherical coordinates where rho is fixed between A and B, theta is fixed between alpha and beta, and phi is fixed between C and D. Essentially, we're making sure that all of our parameters are not defined by functions, but just by constants. So if we look a little bit at this diagram of a spherical wedge, kind of imagine taking a basketball and kind of cutting it into your best rectangle that you could, which, would not really work very well, but that's kind of how I imagine it, at least. But we have a change in all of our parameters, where we have our change in theta, which is this, the projection of that onto the xy plane, kind of like our sweeping in one direction, where delta phi is our change for this region. Phi is defined from one angle to another. So in this, we could imagine maybe this is going from 20 degrees to 40, 50 degrees, whatever, as phi changes. And theta is a very, very small slice, maybe... I don't know, 70 to 80 degrees. I'm just sort of making numbers up to sort of imagine what these parameters could be in this scenario. And also, rho is the actual radius of our sphere. So coming from here to here, it's kind of like defining it this way. And again, this is very analogous to a box in a triple integral for x, y, z, where it's, we're just taking a literal box. Here, this is like our spherical version of a box. And all of our boundaries of our integration will be constants. And like we've explored with polar, spherical, and even rectangular coordinates, cylindrical, regardless, we can also put functions into these bounds, which we'll get to in a future example. But anyways, much like before, we need to change our, if we're trying to integrate some function of x, y, z, we need to change them into the variables of form rho, theta, and phi. Again, using our fundamental relationships. So notice this is just x is equal to that, y is that, z is that in spherical coordinates. And again, to make sure we're translating from dv properly into our three variables, we need to multiply by something, kind of like we had r dr d theta in polar, which we'll revisit y a little bit later. Let's get into an example. So in this example, it says evaluate the triple integral across region E of yz dv. So we have our three-dimensional surface equation integrating kind of like we looked at with the box example, where we can imagine we have some regions of space E, where within that region we're trying to count the density, essentially how many particles are in that based on our function, and we're integrating across the full volume, differential volume. And it says where E lies above the half cone phi equal pi over 3 and below the sphere rho is equal to 1. So one way to define a cone, I know we define cones using rectangular coordinates back in chapter 12, but they're actually fairly simple to do in spherical coordinates, because if we just fixate the phi parameter, remember phi is the angle that our curve takes with respect to the z-axis. If it's stuck on pi over 3, which would be 60 degrees, essentially what we get is a fixated region which must have a very specific angle to the z-axis. So in this cone presented on our lecture notes, it looks kind of like maybe it's 20 or 30 degrees, but for say pi over 3, we'd have essentially a 60-degree spread, and we'd have a fairly spread out cone. And since it's fixed for all other parameters, we would get the essentially equation of a cone. It also says below the sphere, rho equal to 1. So in our lecture graphs, I've provided a diagram of this, which we'll open in a minute. But essentially, notice how our angle from z-axis down to the cone, which the cone is kind of in brown here, like our ice cream cone, which is why I chose brown to sort of make it seem, because essentially this problem is sort of like finding how much stuff is in an ice cream cone. We have a 60-degree angle here for our cone itself. But also, in our sphere, which is in blue, so imagine we're having blueberry ice cream or whatever. Imagine we filled our cone up with a nice scoop that, sticking off the top of that cone. And in this question, that's essentially what we're trying to find. What is well, we could find the volume above the cone and beneath the sphere using a triple integral of 1. But in this case, we're going to do even more by integrating across a function. But primarily, we're using this example to see how we can actually triple integrate within spherical coordinates. So let's go ahead and get it set up. So, let's just write out our triple integral across region E of yz with respect to the volume. And again, since this is actually a spherical wedge, I didn't really talk about why that's the case yet. But essentially, rho, we're going to be going from 0 to 1 because we're trapped within a sphere of radius 1. So our boundaries on our rho part, aka A to B, should just be 0 to 1. Now theta is the rotation about the xy plane, kind of our normal theta value. Since we're doing a full circle in this whole ice cream cone, right? We're doing the whole cone, not kind of half a cone. Theta will be from 0 to 2 pi. And phi, since we're within the ice cream cone, reminder, 0 starts at the z-axis for phi and goes out to pi over 3. So In this case, our boundaries will be relatively straightforward. We're going from 0 to pi over 3 to stick within the ice cream cone. We're going from 0 to 2 pi to do the full circle of the cone itself, or the sphere, whichever one you want to look at it with respect to. And then we're going from 0 to 1 from rho. And again, we want to make sure our variables are changed into polar coordinates. So again, x is this, y is this, and z is this. So our function here is y times z. So for y, we're going to have rho sine phi sine theta. And for z, we're going to have rho cosine phi. And then this will all be multiplied by rho squared sine phi d rho d theta d phi as we translate it into our full integral. So pretty long integral. But what's nice here is that we have a big series of components. And since this is actually a large product, we could actually separate these integrals into three single integrals, a product of three single integrals by the factorization theorem, which I know it's been a couple weeks since we actually looked at that. We haven't actually done an example of that. But since there's no plus or minus, since there's not multiple terms here, I mean, when we have multiple terms, we could also separate them out. But when we have a massive product, that can make things a lot easier. So let's go ahead and just do that to make our integral a little bit easier in a step-by-step manner. So let's just kind of keep it in the original order. So phi is integrated from 0 to pi over 3. And we can put all of our components that involve phi into the first part. So we have sine squared phi, because we're going to have a sine. So let me actually underline all this. Everything that involves phi is here, right? So throwing that all together, we would have sine squared phi cosine phi d phi. And this will be multiplied by our integral from 0 to 2 pi of everything involving theta. Notice that of theta, all we have is a sine theta. So we're integrating sine theta from 0 to 2 pi with respect to theta. And then that would all be multiplied by 0 to 1. We have rho times rho squared. So we're going to have a rho to the fourth with respect to rho. And this will make our life easier since we don't have to iterate that 3 times. We can just do each component separately as it is a full product. Now thinking about each integral, the last two are not going to be too bad. This one involves a combination of trigonometric functions, which is pretty common when we're working with polar, spherical, and cylindrical coordinates, right? That's just how it is. So we could always go back into our Calc 2 notes to think about these things. But a lot of the time it will involve a U substitution or some form of an identity. So how I usually would solve these is think about, does a simple U sub work here? And anytime there's a singular, like a cosine or a tangent by itself, it can be helpful to think about, okay, what's the other paired function, like in this case sine? And if we set U to be sine, then du will produce a cosine. So it's actually a relatively simple substitution here. Let's write that on our margin. So we're going to set U to be cosine phi. Sorry, I said it correctly and then I wrote it wrong. U is going to be sine phi. And you can always just try one, see if it works. And if not, try another one. And then this will make du have to be cosine phi d phi. And summarizing, this will all be our du component, and this will be U squared. So let's write that all out as we perform our U substitution and change it here. So we're going to have an integral of U squared du, and then our boundaries, again, we can't forget to change those either. So sine of 0 should be 0 as well. Thinking about our unit circle in the first quadrant, right? Sine is always y, and at the initial point, we have nothing. And then when we get up to pi over 3, which is at 60 degrees, sine will be at root 3 over 2 at that point. So we're going to have root 3 over 2 as we change those boundaries here. Okay. And so in our second integral, we can go ahead and solve these last two because we won't have to do any substitution. Antiderivative of sine is negative cosine. And so that would need to be integrated from 2 pi to 0. And the integral of a polynomial or a power function will be using the power rule, add 1, drop the reciprocal from 1 to 0. So that should all... Now looking at each component of these integrals, the last one we have a polynomial, right, which we would have 1/5 minus 0. So it's just going to be fractional. Over here, we're going to have root 3 over 2 squared or cubed, also going to be fractional or, you know, irrational, but a fractional expression. Now, but looking at the middle, if we're thinking about our cosine function evaluated from 2 pi to 0, well, the cosine of 2 pi is 1, as is the cosine of 0. So if we pay attention to our signs in here, right, we're going to have negative 1 minus a negative, minus a negative 1. Because, right, we're going to have the negative from plugging it in, and we're going to subtract from the fundamental theorem of calculus, and then when we plug in the 0 again, we have the negative as well. Or what we notice is we're going to have 0. And so 0 times whatever these fractions are, and whatever those fractions are, ends up we're going to have a total of 0 from this integral. Now, this would be something that would always be concerning to me if I didn't know the problem very well. But if we actually go back and look at this object, we had our ice cream cone and we're trying to figure out how much stuff was in here. But notice the density function involved y. And if we think about the overhead look on the y-axis here, let's actually sketch this out so I can use the diagram to talk about this. But if we're looking at the xy plane, we have a circular cross section here for our ice cream cone that we're kind of stuck within. But if we think about the density function y, what this is saying is, well, the density is modeling with y itself. So like as we move in the y direction, it would start at 0. Essentially, there would be no density in the middle, and it's going to get more and more dense the further we move up that curve. And similarly, it's going to actually be negative if we go the other way because it will have a negative y, right? So like down here, it's going to be really densely negative. And here it's going to be a little less dense and so on. But the density is a linear function of y in the y direction. I'm ignoring z here because this is essentially y at 0. The positives and the negatives are going to cancel out. So actually the 0 ends up making sense here. So let's say instead we just wanted to calculate the volume within the ice cream cone because that's a little bit more of an interesting question. It's actually going to be an easier problem because all we would have to integrate is 1 dv instead, because the triple integral of 1 with respect to the volume will provide the area of region E. Let's actually do that in the next example just for fun.